Okay, so welcome to this video on the intermediate value theorem and its proof. So firstly we're going to state the intermediate value theorem and then we're going to prove it. Okay, so it has a huge number of applications, especially it is really the most important theorem about continuous functions as far as real analysis is concerned. So the concept of a continuous map that is one that extends beyond real analysis. It's actually a topological definition, where it can be extended to a topological definition. But in this video we will just consider it, we will just consider continuous functions on the real line onto the real line. So let us begin. So the intermediate value theorem. The intermediate value theorem. Sometimes abbreviated to the IVT. Okay, so the intermediate value theorem. So let f map the real numbers onto the real numbers. In fact, it doesn't need to be quite that big. We could limit ourselves to some closed bounded interval AB onto the real numbers. So the picture is that we have some, it could be the whole, you could let the interval be, you know, the whole real numbers, but we could just limit our interest to a smaller section of the real line. So if we have some interval here, which is topologically the same, well, it's topologically the same as the extended real numbers, but if we had an open interval, it would be topologically the same as the large real numbers. That's not really that important, but we want it obviously to be connected. We want to consider an interval that's connected. If not, just limit your attention down to one that's connected. Okay, so as long as our function is obviously it can be extended, this result can be extended, but in its most basic form, we'll just take this. So we have this interval AB, and we're going to map it onto the real numbers like this, like so, and it's continuous. So f is continuous, and the intuitive definition of continuous is what I've drawn, that you can draw it without taking your pen off the paper. There is a very rigorous definition of continuous, which is that if you take any point here, so let's take any x, take an x which is an element of AB. So some value of in the domain of your function. It has a value. The function gives it a value, so f of x. And the definition of continuity at this point. So if f is continuous at x, then the definition of this is that for all epsilon greater than 0, you can find a delta greater than 0, such that if y is an element of the ball of radius delta around x, then it implies that the ball of that f of y is an element of the ball or around f of x of size epsilon. So that is a bit of a mouthful, but it has an incredibly intuitive picture. So okay, so basically you give me any epsilon, I will construct you a ball around here. So this is my point f of x. So we want a ball of radius epsilon, so it's an open interval around f of x, because this is quite a simple metric space. Obviously this is generalizable to an abstract metric space, but as far as just this is concerned, then we just need an open interval around here of length 2 epsilon it will be. So the distance here is epsilon and the distance to here is epsilon, so the overall length of this interval is 2 epsilon. You give me any epsilon you want, so I can make this as small as I want. I'm telling you that I can find you a delta such that this ball of size delta around x, so the ball of size delta around x, any element in that ball will be mapped into this interval over here, basically, which is what f of y is an element of this ball over here. So basically I'm saying, take this interval as small as you want. I will be able to find you an interval small enough over here such that the entire interval is mapped into there. So basically, it's almost like saying that that these intervals around x are converging on f of x, because it's like saying that if we take this sequence of intervals, so if you have the sequence of intervals getting smaller and smaller here, then there is some point after which all of them are within an interval around here of whatever size you want. So it's almost saying that the intervals here converged there, and that's kind of what it is saying. So that's the rigorous definition of continuity. So the intermediate value theorem is then that if this holds, then if you have 2 points in AB. Let us say, for argument's sake, let's call them C and D. C and D are elements of AB, and let's, for argument's sake, without loss of generality, we'll say that C is less than D. So the picture is that we have our interval here, A, we have some C, we have some D, and then we have some B over here. Well, the end of the interval here, B. And C will have a value which is f of C, and D will have a value which is f of D. So here we are. So basically, the intermediate value theorem states, the intermediate IVTR, we'll abbreviate it to, says that there exists, what should we call it? An E? No, we won't call it that. We'll call it a G, which is an element of CD, the open interval between here. So there's a G in the middle here, such that f of G is whatever value you want between f of C and f of D. So basically, I've stated this badly. It says that let me state it differently. That if let's say something. If H, rather, no, I'm going to say if H is without loss of if H is between f of C and f of D. So we don't know. I've drawn it as though f of C is bigger than f of D, but that's f of C, we don't know which one is which. This one might be smaller than this one. So if H is between f of C and f of D, so in this case, if f of C is greater than f of D, then H will be greater than f of D, but less than f of C. So it'll be in between them. Or if it's the other way around, if f of D is greater than f of C, i.e. this one's up here and this one's down here, then H is going to be greater than f of C and less than f of D. So just in between them, basically. Then there exists a G which is in between C and D, which is an element of CD, such that f of G is equal to H. And I feel like I've made that into something difficult when it's not really. It's just saying that you take any value between these two values, and I will find you. So I will find you a G such that a G which is in between here, such that the function goes through that. So basically, it's saying that if you have to draw this between here, at some point it must cross any line which you draw between them to get down to here. That's all the intermediate value theorem is saying. Now you may think, oh gosh, how trivial, but proving that in terms of this abstract definition up here is more difficult than it would seem. It's obviously very intuitive when you think of continuity as drawing it with a pen without taking it off the paper, but proving it in terms of that isn't so trivial. So that's what we're going to do now. So proof, and we're going to use a technique called what are we going to use? We're going to use a technique that that when I was lectured by a guy called Timothy Gowers, who taught Analysis 1, and he called this continuous induction, so that's what I'm going to call it. So we're going to use continuous induction. Now, it's like a continuous analogue of induction. I didn't know actually what the correct term for this method is, but continuous induction seems a sensible name, so we're going to call it that. Okay, so firstly, what I want to say is that without loss of generality, let's assume f of c is greater than 0 and f of d is less than 0. So basically what I'm saying is if we have this here and this is c, and this is f of c up here, and this is d, and this is f of d down here, then there exists a g which is an element of CD, the open interval CD, such that f of g is equal to 0. That's a better statement of the intermediate value theorem, that at some point it will cross this line, because understand why that is exactly the same as what we've done up here, because if this is true, that's true too, because all I have to do is bring this down a bit, and then this will cross the x-axis, and you know, if this was a continuous function, then if you just move it down, it will still be a continuous function. Therefore, apply this theorem here, and it will imply this one up here. On the other hand, if it turns out that f of c is less than f of d, then all you need to do is flip them round. You need to multiply them by -1. Well, bring them down first and then multiply them by -1. But it will, or you can multiply them by -1 and then bring it back up if you like. The point is, those operations will leave the function continuous, and therefore you can apply this theorem, and then that'll just, you know, pulling it back in a way, it will imply that the original problem you were trying to solve was true. So we will only need to prove this, that if you have one function one value up here, one value down here, then at some point it crosses the x-axis. Okay, so how are we going to prove that? Well, the way we're going to prove it is we're going to proof by contradiction. Firstly, it's going to be a proof by contradiction. So, okay. Therefore we suppose that for all x is an element, I'm going to move this up a bit, x is an element of AB, x, yes, it can be the closed interval if we want, for all x is an element of AB, f of x is not equal to 0. So we're going to, okay, that's the negation of our statement, that nowhere it is equal to 0, so it never crosses the x-axis. What we're going to prove from this, we're going to use the fact that, plus the fact that it's continuous, we're going to show that it must always be positive, or it must always be negative. In this case, it must always be positive is what we're going to show. Okay, and we're going to use continuous induction, and this is how we're going to do it. Okay, where do we go from now? So, we want to show that f of x for all f of x will be greater than 0 for all x is an element of AB, this implies. And how we're going to show this is, we're going to the first starting point is alright, how am I going to do this? This is the statement, basically. The way we're going to apply continuous induction is that we're going to say, if it's true here, because we know it's true here, we know that f of c is greater than 0, we're going to say that now we know it's there, we're going to show that it's true for a little bit more, basically. And then what we're going to do is show that if it weren't true, if it was less than 0, that would imply that for a little perturbation this way, it was less than 0 as well. And what we're going to show is that that proves that it's going to be greater than 0 for the entire thing. So if it starts off greater than 0, and it never is equal to 0, then it must always be greater than 0, is what we're going to show by continuous induction. So, okay, I'm trying to decide whether it's better just to show you continuous induction and then apply it, or whether it's better to just show you continuous induction within the proof. Okay, I'm going to show you continuous induction first, I think. Okay, so because it's simpler to show you continuous induction rather than do it with this more complicated statement. So if we have a statement, we have a statement like P. Statement P. So P is either true or false. P is true or P is false. True or P is false. So actually I will sort of like show you how this is going to apply to our example within it. So in this case, P is going to be the statement that f of x is greater than 0. So at every single point along this interval, CD, I can say whether it's greater than 0 or whether it's less than 0. So the statement that is greater than 0 is either true or false. We know that f of x is not equal to 0, so we don't have to worry about that. The function is either greater or less than 0, so this statement is either true or false. Right, okay. So P is true or P is false at every point along this interval. If we can show, okay, so firstly, if P is true at C, and we can show that P being true at C, implies there exists an epsilon greater than 0, such that if let's say if x minus c is less than epsilon, so x is some value just in front of here. So if it's within epsilon, so you can find an epsilon such that if this x is close enough to c, closer than epsilon, that implies that P is true for x. So there exists a little bit in front of it where the statement is still true. P is true for x. Also, if we can show, oh sorry, this isn't necessarily just for C. This is if it's true at any point, if it's being true at any point P, any point little p rather, no, I shouldn't use P again, any point little q, there exists an epsilon such that if x minus q is less than epsilon, that implies P is true for x. Okay, so I'm saying basically if it's true at any point, I can find an epsilon neighbourhood such that in front of it, by that epsilon, it's true on there as well. Okay, also, if we can show that if it isn't true, if P is not true, if P is not true or at let's say q bar, then there exists an epsilon greater than 0 such that if q bar minus x is less than epsilon, that implies P is not true on q, not true at x. So basically I'm saying that if it's not true at some point q bar, let's say, then there will exist an epsilon down here such that for all that bit it's not true here either. Okay, so here's the trick then now. Continuous induction is going to, now, if you can show this, then what can we do? We can go forward, we can say there's an epsilon around C where it's still true. So we do that. Then, at the boundary point here, the epsilon property didn't give us that it was still true there, because it's within this is an open interval basically. We don't know that it's true at C plus epsilon, but we do, because if it were not true at C plus epsilon, then there would have to exist an epsilon the other way, such that it wasn't true, and there can't be, because for every single, this is a limit point of all these points where it's true, so whatever size neighbourhood you take around here, you can't possibly get a neighbourhood where it's utterly non-true. Therefore, at this point, it will have to be true as well, and therefore you can go on and on and on, and this process induces itself basically, and there are a few sort of little details that you have to nail down and convince yourself of here that are quite, they're not trivial, because it's not trivial that what's not going to happen is, you know, you're not going to get this, and you're not going to get intervals that sort of converge on and converge on and converge on and converge on, but never actually get past some point here. But what will happen then is that they will converge onto here, and it will be true for all of this bit, and you won't be able to say whether it's true or not for them, but then you apply this one again, and you'll go on and on and on, and you can show, it's a bit more work, but you can show that if this is true, it implies that, that it's true on the entire interval. How would you do that? The reason I'm skirting around having to do that is I've kind of lost sight of how you would go from there to actually prove the point. That's how you do prove it. Let's think. If x is so, let's complete this. Let's have a go at least trying to complete this. I might have to give in, but so what we know is that P is true at C. Let's proof by contradiction, I presume. Proof by contradiction. So we want to prove that if those two previous properties we've just observed, we want to prove if those two previous properties hold, P is true on CD, on the whole interval, basically. So we're going to do a proof by contradiction. We're going to assume not, then P is not true somewhere. Okay, right, why does that lead to a contradiction? Well, we can apply property 2 and say that there's then a neighbourhood where it's not true. How would you do that? I might have to cut the video and think a bit more, and then do part 2. Yeah, I will cut the video and I will continue it once I know what I'm doing.